Hi everyone, I'm Yunlin from National University of Singapore. In this talk, I will introduce our work to improve search-based testing with our object synthesis technique. Search-based software testing technique, or SBST, considers automated software testing as an optimization problem. Here, the goal of SBST is to generate test code to cover as many program branches as possible with a limited budget. Given an uncovered branch in a test case, by defining the loss functions to measure how far the test case is away from covering the branch, we can gradually mutate and evolve the test case to cover the branch by minimizing the loss function. And here is an example where the optimization goal is to cover the conditions in red. That is, we aim to generate a test case to exercise a branch conditions where x is equal to 123. SBST approach uses branch distance to evaluate how far a given test is away from covering a branch. In this example, the branch distance is defined as the absolute value of the difference between two operands in these conditions. Therefore, the branch distance is calculated as the difference of 0 and 123. The less the branch distance, the closer a test is to cover the entire branch. More details of the definition of branch distance can be referred in Prof. Phil McMean's survey. Therefore, each test case is actually a solution in the search space. The global optima means the test case can finally cover the branch. However, the challenge of SBST lies in that the search space landscape for a test case is usually neither continuous nor monotonous. With such a landscape, the traditional SBST approach usually stuck on a local optima and cannot cover some branches. And our observation is that one of the most important barriers to make the search-based testing ineffective is the problem of inefficient object construction. SBST algorithms can be much more effective if we can search based on a test case with well-constructed object. Here is an example. Given a branch, the first test case has no branch distance accessible because a non-point exception will happen when evaluating branch expression. In contrast, the second test case has a branch distance, which can guide the search. And we can see that the first test case actually lies in a search landscape with no accessible branch distance, and all its neighbors will have no accessible branch distance either, because all its neighbors will also incur non-point exceptions. In contrast, the second test case can have a branch distance and guiding its evolution towards the global optima. However, the state-of-the-art technique has no guidance to evolve from the first test case to the second test case. Note that in such a case, the test case evolution will degenerate into the random testing. And we propose EvaObject to address these problems by synthesizing the test seeds with well-constructed objects. The rationale is that we try to synthesize a seed which is more likely to near the global optima. Based on this test case, the search with such a seed will become more convenient. If we want to construct an object based on a branch, we need to answer the following three questions. First, which object inputs are relevant? They can be either parameters, instance views, or even global observables. And second, how complete should we construct the objects? The object structures can be very complicated, such as a hash map or binary tree, and how deep should we construct those objects? And third, given the data structure or the object structure, how can we generate the objects in the test source code? And we answer those questions with 3 steps. The first step is that we construct an object construction graph by applying interprocedure static slicing based on the branch operands. Different from the traditional slicing results, we keep the graph structure while applying the data and control slicing across the program. The graph will start with a method input or input objects and ending with the relevant object state variables. And those state variables including class fields, array elements, and global variables. And the structure between the variable nodes indicating how we can construct a state variable which is relevant to cover a tilde branch. For example, in this pass, we can construct the action by first having the returned object by calling the player methods of the state object, and then we were taking the action field from the return object. When the object construction graph is ready, and we then traverse the graph and then generate the test code based on each node. In this work, we traverse the graph with a breadth-first algorithms. Note that each generated statement will be specified as a slot as a mutation point for the follow-up evolution. Finally, we will adopt the search algorithms, which can evolve the synthesize the test template by mutating those slots. Here, in order to increase the diversity of the test cases, we still allow the mutation like deleting or adding statements during the test case evolution. And our experiment on over 2,000 Java methods show that if object can have non-trivial coverage improvement for even weight and on various search algorithms. In addition, if object will always take a lead in terms of coverage along the time. And here is the takeaway of this presentation. For SPST, the search space is usually neither continuous nor monotonic, so SPST can easily degrade to random testing in practice. And we observe that inefficient object construction is an important reason for such a search landscape, and we propose if object to effectively synthesize object to enhance the test evolution efficiency.